In this video, we shall discuss the optimal property of the ratio estimator. Now, for this, we shall now assume that the population of size n can be regarded as divided into k classes with the ni units in the ith class. Having the value xi each with summation I equal to 1 to k ni equal to n, and that is that in repeated samples of size n drawn from the population with equal probability and without replacement, the number of units having the value xi fixed, say ni I equal to 1 to up to k. Now the second assumption, the ni values are sufficiently large so that ni minus 1 by ni is approximately equal to 1 and ni minus small ni by ni minus 1 is also approximately equal to 1. Now the third assumption, the expectation of yij given xi, that is equal to beta into xi. That is, the relation between yi and xi is a straight line passing through origin. The fourth assumption, we shall take the variance of yij given xi equal to gamma into xi. That is, the variance of yi is proportional to xi. Now consider the subclass of linear estimators of the type t equal to summation I equal to 1 to k lambda I ni y ni bar, where y ni bar is the estimate of y bar from the ith class. From the ith class based upon ni number of units, and all yj observations in the ith class are assumed to have a same weight lambda I, which may depend upon the value of xi but not on the auxiliary, not on the study variable y. Then we shall show that t is the best linear unbiased estimator of y bar. So for this we have to show that T is the blue, best linear unbiased estimator of y bar. For this first, it is, we have to show that it is a linear function. So linear function of observations. So this is the linearity. Second, it is unbiased estimate of y bar. This is unbiased property. Now third condition, third we have to show that it has a minimum variance, that is it is the best. So it is best linear unbiased estimator. So now consider expectation of t, that is equal to summation I equal to 1 to k lambda I ni expectation of y ni bar given n1 n2 nk, that is summation I equal to 1 to k lambda I ni expectation of j equal to 1 to ni yij by ni given n1 n2 up to nk. So that is equal to summation I equal to 1 to k lambda I ni expectation of j equal to 1 to ni yij by ni given the ith value of the auxiliary variable xi. So this will be equal to summation I equal to 1 to k lambda I expectation of j equal to 1 to ni yij given xi. So this is equal to summation I equal to 1 to k lambda I summation j equal to 1 to ni expectation of yij given xi. Now this will be equal to summation I equal to 1 to k lambda I summation j equal to 1 to ni, this will be beta xi using the condition. So that is equal to beta summation I equal to 1 to k lambda I ni xi. So in order to t to be an unbiased estimator of y bar, we should have expectation of t equal to y bar. So that implies beta summation I equal to 1 to k lambda I ni xi, this will be equal to y bar, means this is summation I equal to 1 to k ni yni bar by n. So where yni bar is the population mean of the ith class. Now beta, this implies beta summation I equal to 1 to k lambda I ni xi equal to summation I equal to 1 to k ni expectation of yni bar by n, because expectation of yni bar equal to capital Yni bar. Now this is equal to summation I equal to 1 to k ni, this is beta xi by n, that is equal to beta summation I equal to 1 to k ni by n xi. So that implies summation I equal to 1 to k, cancelling beta both sides, lambda I ni xi equal to summation over I equal to 1 to k ni by n xi. So from the condition of unbiasedness, this minus this must be equal to 0. When t is unbiased, so summation I equal to 1 to k lambda I ni xi minus ni by n xi, this equal to 0. That is summation I equal to 1 to k lambda I ni minus ni by n xi, this is equal to 0. This is equation 1. Now the variance of the estimator t for fixed value of n1, n2, nk is given by variance of t, that is equal to summation I equal to 1 to k lambda I square ni square variance of y ni bar given n1, n2, nk, that is equal to summation I equal to 1 to k lambda I square ni square variance of y ni bar given xi. So variance of, since we have given that variance of y is a given xi equal to gamma xi, so this implies variance of y ni bar given xi equal to n minus ni by ni minus 1 into gamma xi divided by ni. So this is approximately equal to, because n minus ni by ni minus 1, this is approximately equal to 1. So as per the assumption, so this is only gamma xi by ni. So variance of t equal to summation I equal to 1 to k lambda I square ni square into variance of this, so into gamma xi by ni. So this is equal to summation I equal to 1 to k lambda I square ni gamma xi, that is equal to gamma summation I equal to 1 to k lambda I square ni xi. Now we have to determine the value of lambda I so as to minimize this variance of t subject to the condition of the unbiasedness in equation 1. So let us define a function phi equal to gamma summation I equal to 1 to k lambda I square ni xi minus mu whole into mu into summation I equal to 1 to k lambda I ni minus ni by n into xi. So this is the variance and this is the condition of unbiasedness. Mu is the Lagrange's multiplier. So now differentiating with respect to lambda I and equating to 0, we get 2 gamma lambda I cap ni xi minus mu ni xi, this is equal to 0. That implies lambda I cap equal to mu by 2 gamma I equal to 1 to k. So now summation I equal to 1 to k lambda I ni xi, this is equal to summation I equal to 1 to k ni by n xi, that is equal to x bar. So this implies mu by 2 gamma summation I equal to 1 to k ni xi, that is equal to x bar. So that implies mu by 2 gamma equal to x bar divided by summation I equal to 1 to k ni xi, that is equal to x bar by n into small x bar, because lambda I cap equal to mu by 2 gamma, that is equal to x bar by n x bar. So this implies this. So the best linear unbiased estimator of y bar is given by t, that is equal to summation I equal to 1 to k lambda I cap ni y ni bar. So that is equal to x bar by n into x bar summation I equal to 1 to k ni y ni bar. So that is equal to x bar by n into x bar, this is n into y bar. So this is y bar by x bar into y bar, that is the usual ratio estimator y r bar. So under the given conditions, our usual ratio estimator y r bar, that is equal to y bar by x bar into capital X bar, is the best linear unbiased estimator of the population mean y bar. So we can write a theorem like this: with SRS with simple random sampling from an infinite population, the ratio estimator of y bar is a best linear unbiased estimator, that is blue, if the following two conditions are satisfied. One, the relation between yi and xi is a straight line through origin. Second condition, the variance of yi about this line is proportional to xi. So these two conditions are called as the conditions of optimality of the ratio estimator. Now in my next video I shall consider the double sampling in ratio estimator. Thank you.